is the second thing now. Now, okay, so suppose you have F containing K containing L. Now, suppose K is a splitting field over F. Over F. Okay? Now, what we discussed earlier was that then, so recall, that now, if I take every element of the Galois group of L over F, any automorphism of L that fixes F, that will send K to K. And it's going to give us an element of the Galois group of K over F. So you have this restriction map, from the Galois group of L over F to the Galois group of K over F. Right, so this is just sending sigma to what I'm going to denote by sigma sub K, which is just, well, sigma, but considered only on K. Restriction of sigma to K. We call it restriction to K. I think this is what we, this is the notation that we used for it last time. Okay, so you have this. Now, suppose, so here's the proposition. Suppose, in addition, that L is also a splitting field over F. So we were already assuming that K was a splitting field over F. Now, in addition to that, assume L is also a splitting field over F. Okay? Then, the restriction map star, the map star is surjective Okay, let's prove this statement. So this is another application of theorem 51. So what you do is the following. Okay, so what are we trying to do? We're trying to prove that this map is now surjective. So you give me an element of the Galois group of K over F, and I want to say that, well, it's an image of this map. So what does that mean? That means that it extends to an element of the Galois group of L over F. So given tau in the Galois group of K over F, you need to show that tau extends to an element or extends to an automorphism of L. Alright, so this is your picture. This is now, you've got K. If I write over there, can you guys see? I think so, yes. Okay, so your picture looks like this. You've got K to K. This is tau. Fixing F. So I put equality here, by which I mean you've got the identity map here. And so tau is extending the identity map on F. And what you want to do is that you want to extend tau to an automorphism of L. Right? If you can extend tau to an automorphism of L, then the restriction of that automorphism of L to K will be just tau. So now, sorry, I'm just going to make sure that we're not losing the camera. And now, okay, so how do we do this? You're going to use the theorem 51. So suppose, see, what did we assume? We assumed that L was the splitting field of was a splitting field over F, right? So let's say L was the splitting field of some polynomial, so if L is the splitting field of some polynomial f over f, then of course L is also the splitting field of the same polynomial over k. Right? So L is the splitting field over k, and now theorem 50 tells you that this automorphism of k extends to an automorphism of L. So L is also a splitting field over k. If it was the splitting field of a polynomial, let's call it g, just so that you know we don't have too many f. If L was the splitting field of g over f, it's also the splitting field of the very same polynomial g over k. So L is also a splitting field over k, and now just apply theorem 51. You've got an automorphism of k. L is the splitting field of some polynomial over k. This isomorphism from k to k extends to an isomorphism from L to L. In other words, extends to an automorphism of L. So theorem 51. So theorem 51 guarantees that tau extends to a tau hat. Extends to an automorphism tau hat of L. So that's it. Right, so you're applying theorem 51 to this side, the upper half of the picture. Okay, you're applying theorem 51 to this diagram here. You've got an automorphism of k. L is the splitting field over of some polynomial over k. And then you apply theorem 51 and see that this automorphism of k extends to an automorphism tau hat of L. Okay. Very good. So I think, let me see if there's anything else that you want to include in this video. Yeah, so I just want to maybe recap this result. That the result was that if you have, let me write it down here. So if you have a diagram like this, L, K, F, and this one you know is a splitting field, then, well, so you've got the restriction now from Galois group of L over F to the Galois group of K over F. And now, if you assume that this is also a splitting field, so I have this, and now if L over F is also a splitting field, more clearly, let me say, if L is also a splitting field over F, then this is surjective. Okay, so that's what we prove. By the way, actually, maybe let me also add a remark here that in general, what's the kernel of the star? So in general, so even if you don't assume that L is a splitting field over F, what's the kernel of this mapped star? So let's just think about this for a second. These are automorphisms of L that fix L. Okay, so what was this map? You're just restricting to K, right? So what's the kernel of star? Okay, so what does it mean for an element here, for an element sigma here, to be in the kernel of a star? Well, the kernel of a star, the identity element of this group is the identity map on K. Right? So now what does it mean for something to be in the kernel of a star? So take sigma in the Galois group of L over F. What does it mean for it to be in the kernel of a star? It means that when you restrict it to K, you get identity. In other words, sigma acts trivially on K. which is the same as saying that sigma actually belongs to the Galois group of L over K. Yeah, so no, in general, when I say in general, I mean you don't need this L to be a splitting field for this statement. The kernel of the map star, that restriction map, is equal to the Galois group of L over K. Okay, very good. Let me stop here. Thank you.